Hello, my name's James Kermode and I'm an academic in engineering at Warwick. In this short video I'm going to tell you a little bit about my research, which is in the field of computational materials engineering in my research group in the Warwick Centre for Predictive Modelling within the School of Engineering at Warwick. In particular, I'm focused on describing materials right down at the atomic scale, so looking at individual atoms and bonds and trying to use that to understand how materials break through a process called fracture. There are a number of different example systems that I've worked on, and the thing that they have in common is a combination of chemistry, so breaking of chemical bonds right down at the atomic scale, looking at individual bonds breaking apart, and mechanics, so chemomechanics together. And mechanics means the application of forces or stresses far away from where the material is actually breaking up. So if you think about a typical thing breaking, the forces are applied far away and their load is concentrated right down on a tiny microscopic region where chemistry happens and bonds break. A few examples that we'll look at in this brief presentation include fracture of drill bits that are used, made out of diamond and used to make extremely sharp cutting tools. Friction is closely related to fracture, so rubbing a tiny this is a tip of an electron microscope rubbing on a surface and trying to measure the roughness of the atomic scale surface underneath. And then moving up to larger scales, we might be interested in trying to understand how to break up rocks out of the ground when they've been dug up in a mine without having to put too much energy in. So reducing the energy cost of mining by trying to understand the underlying fundamental processes that are involved in breaking materials down. Rocks actually have a lot in common with materials such as glasses. The structure is very similar, and glasses are a bit easier to look at in the laboratory. So the sort of most obvious example of what's called a very brittle material is glass. We'll look at that a little bit more in a minute. More recently, I've also been looking at metallic systems, so trying to understand things like superalloy turbine blades that are found in jet engines. So there's a picture of that up on the top right here. This is a turbine blade within an aircraft engine. It's actually made out of a single crystal of materials. So inside the turbine blade, it's grown in a mold. All the atoms are lined up perfectly in a perfect crystalline lattice. And that means that it's really important to understand the processes right down at that atomic scale to be able to design and improve future generations of alloys. The last example down at the bottom right is future materials for making fusion reactors, or in particular for shielding the outside of the fusion reactor. The material that's used for this is tungsten. It's the only thing that can cope with the massive amounts of heat that a nuclear fusion reactor puts out, but we have to understand better how to make it strong enough to last for a very long time in those very challenging radioactive conditions. So let's look a bit more at what's going on when something breaks. This is what I found when I came into my office a few weeks ago. A massive crack through the glass wall. You can see that it's really broken up into tiny pieces. If you zoom in on those individual cracks, then what you'll find is that they're really sharp, and you can actually zoom in right down to the atomic scale. So this picture on the bottom left is an atomic force microscope image. It's not actually an image of my door, but it's of a similar piece of glass, and it's down at the 500 nanometer scale. So that's half a micron in scale, and you can see that the crack shown in green inside is really sharp, right down at the atomic scale. In my case, I think the problem that had gone wrong was there were some residual stresses left in this big window after it had been installed. So it wasn't quite straight, and there was a stress there that eventually became critical, and then cracks just exploded throughout the material. We'd like to understand how that can happen, what might cause it, and how it could be prevented in future. The other example, the other kind of fracture that I'm interested in is called ductile fracture. So that's what typically occurs in metals, where you pull on a piece of metal and it gets thinner in the middle and then eventually separates into two pieces. If you zoom in on what's going on inside a ductile fracture, you find it's quite different to the very sharp brittle case that we see in glass. Instead, there are lots of little holes called voids that grow inside the material, and eventually enough of those holes combine and make a critical size void, which causes the material to fail. So it's quite a different process. So far, most of the modelling I've been doing in my research group is focused on the brittle side of things, on the side where it's very, very sharp, because it's easier to describe what's going on there with atoms. Another kind of material defect that we might be interested in is called a dislocation, and that is like a mistake in the layout of the atoms that make up a crystal. There are two different types, edge dislocations and screw dislocations. In an edge dislocation, you can think about there being an extra row of atoms that shouldn't be there. So on the left-hand side, you can see with the solid black line an extra row of atoms in this crystal that cause a mistake in how it's laid out. The other type of dislocation is a little bit harder to visualize. That's called a screw dislocation, and that's where the shift is instead in the other direction, in the out of plane direction, and the atoms instead have a mismatch in that they've been pushed backwards on one layer. If we look in real materials, we can find very close analogies or very good pictures. This is a microscopic image of what an edge dislocation really looks like, and you can actually resolve the individual atoms. This is a transmission electron microscopy image, TEM image, and you can really see the atoms that form this dislocation. You also find them in more realistic examples in things like brick walls. So if you look at this wall here, you can see that there's a mismatch in the layers of bricks and they don't line up properly. So on the right there are two rows that become just one row on the left. You can also find them in the natural world, things like cactuses. So this cactus here you can see has got an edge dislocation in it. In the top half there's an extra row of spikes compared to the bottom half. So these are all the kinds of phenomena that occur on all different scales, but in my research group we focus on trying to understand them right down at the bottom, right down at the nanoscale. And we use a range of different modelling techniques to do that. I'm going to give you just a couple of quick examples of the kinds of things that we might be interested in doing. So one way to model things is to use balls and sticks to represent the atoms. That's quite useful, but not very accurate. We can model maybe 1 million atoms in that way and get a description of what's going on. So for example, we might be interested in looking at these dislocations that I was talking about inside a jet engine turbine blade. So this is a simulation of the inside of one of those superalloys, where we might be interested in trying to understand how dislocations move around. So let me just play the movie again. Dislocations move around inside parts of the material. Here we've got a separation into two different types. It's a bit like bricks and mortar that make up a wall. The superalloy is made up of a gamma phase, shown on the left-hand side, where my dislocation is moving around, and a harder gamma prime phase which has got extra aluminium in it and is tougher, and the dislocations can't get inside that part. And we'd like to understand why that is and improve the properties of the material and improve the accuracy of the modelling as well. In terms of fracture, we'd like to understand how cracks propagate. So we know from experiments that the cracks should be completely sharp, like in the picture on the left. But if we run a simulation just using one of these simple interatomic ball and stick models, we don't get a very good description. We see that instead of being completely sharp, this crack gets a bit blunt and gets messy. We see all of this nasty triangles and other shapes of atoms around here that we'd prefer not to see. This isn't a good model of what's going on in reality. And in that case, we have to go up to another level of accuracy. We have to use something called density functional theory, which is a model where we include not just the atoms as balls and sticks, but electrons as well. So thinking about how the electrons stick the atoms together. We can use that on its own. It's quite useful for predicting how hard you have to pull to break something. So this is a piece of silicon carbide. We did some calculations where we looked at how hard you have to pull for it to break, and then some colleagues at Imperial College in London did experiments and found a really good alignment between the measurement they made of the fracture energy, how hard you have to pull to break it, and then the calculations that we did using this quantum mechanical DFT simulation. But it's not always possible to separate things out like that and to do a big simulation for not very accurate situation, or a small but very expensive and very accurate simulation. Sometimes we need to put the two together, and that's something I've specialized on in my research group. So we've worked on, for example, sticking together a quantum mechanical description of a system shown here with the blue atoms centered on a cracked tip, combined with a classical description of the rest of the system where not so much interesting is going on. And that's been very useful for describing complicated systems where we might have lots of things happening at once. So this is a good example. Here I've got a crack tip that is running around and being driven towards a dislocation. So I've got both types of defect in this material, a crack and a dislocation. And what we see actually is that the crack gets pulled down towards the dislocation core, and then eventually it annihilates the core, it makes it go away, and then takes a diversion up the stacking fault, which is a weak plane, weak interface in the material. So here we're using the computer to really predict what we would expect to see in reality if we were able to zoom in this far and take pictures very quickly. The last example I want to show you is what happens if you put water or oxygen, if you put molecules into the situation. They can actually react and perform chemical reactions which can break bonds when otherwise you wouldn't be pulling hard enough to do so. This is called stress corrosion, and it's what happens perhaps in the glassy door that I showed you at the beginning. So in this case we've got a molecule of oxygen that's coming in, let's just see that again, and causing bonds to break when otherwise we wouldn't be pulling hard enough for them to do so. This makes cracks propagate very, very slowly because we have to wait for another molecule to get there before the next bond breaks. Okay, that's pretty much all we've got time for. So I want to finish up with a few takeaway points, but first, take care not to forget to thank all of the financial supporters of the research that I've described to you, which includes UK funding agency, the EPSRC, the Royal Society, the Leverhulme Trust, European Commission, and also very large-scale computing facilities that are needed to carry out the kinds of simulations that you've seen in this brief video. So Archer is the UK national computer facility. Actually, it's just being replaced by a new machine called Archer 2, and I've also had computer time at the US and from the European Union under the PRACE initiative. So what are the main messages I'd like you to take away from this brief masterclass? First of all, an understanding that the way things break or fail in other ways is dominated by what happens at very tiny nanoscopic scales, so intrinsically involves separating atomic bonds, which means we need to understand the chemistry of atomic bonding, and that's controlled by the electrons which sit between atoms and bond them together in a covalent material or in a metal, which are delocalized throughout the entire metal and control bonding in that way. I want to hopefully convince you that computer modelling is really important for describing these processes. It's very hard to do experiments right inside something that's breaking, very complicated and expensive to do in situ experiments, and so modelling plays a very important role in our understanding of these kinds of processes so that we can in future reduce the impact of things breaking in unexpected ways, design materials to be stronger and longer lasting, and also to allow us to make use of new materials as they're discovered. If you want to get into this kind of area of research, there's lots of different ways of doing it. So the research that I've described fuses knowledge and expertise from many different undergraduate degrees, in particular physics, chemistry, engineering, materials science, and even some mathematics as well. The algorithms that we use to carry out our simulations benefit a lot from insight from applied mathematicians. So any of these undergraduate degrees would be a great way to get into this field of study if you're interested. Do take the opportunity to find out more about the topics that we've discussed. Wikipedia is a great starting point, especially if you follow it up with some of the linked articles and references, but researchers like me make great use of Wikipedia, so don't feel like it's not an appropriate place to research. But you can also discuss it with your teachers or with your family, and I'm sure there'll be lots of interesting conversations that you can have after all of the interesting videos you'll see as part of this masterclass.
Hiya, welcome to this 10-minute talk about studying physics and engineering at university from the perspective of me, an engineering student from Wales. So my name's Thomas. I'm an engineering student at the University of Cambridge. I'm in my 4th year now. And I come from Ynys Môn and went to school in Bangor and a school called Tryfan, where I studied maths, further maths, chemistry, physics, and the Welsh back. And it's worth saying, actually, that I hadn't decided that I was going to go and study engineering at university, or that I was going to apply, until probably the end of year 12. And before then, kind of maths and physics were still very much on the table. I considered all manner of science subjects, really. Beyond being pretty good and enjoying maths and physics and stuff at school, my interests were in renewable energy, and so I very much approached engineering with that angle. It's worth saying I actually applied to general engineering courses or integrated courses because I couldn't decide if I wanted to study mechanical or electrical or aeronautical engineering, etc. And maybe that's a question that's on some of your minds, and maybe that's something I can help with in this talk. So these subjects that I'll be covering boil down more or less to physical natural sciences and engineering. And there are some universities where you can basically just go to study those very broad subject areas, and then of course you specialise as you go on. So Cambridge, with both natural sciences and engineering, is an example of that, where I study. And some other universities you'll maybe start a little bit more narrow, studying with chemistry or physics, or studying mechanical engineering or civil engineering right from the get-go. Although in my experience, actually, studying this kind of choosing universities with these broad scopes, it doesn't tend to mean that you lose that much in terms of depth, because actually that kind of first year content, when you study kinds of everything, there's a huge amount of overlap, and the same basic principles, the same basic methods are used in all of them. Computer science, I suppose, is another one, but I mean the kind of programming skills, just like with maths, are things that you will learn in a physics and engineering course just as much. Although if you're really, really interested just in programming and computers, go and study computer science. If you're really, really interested maybe in the fourth dimension or in proving theorems, then I think a maths course is more for you. If you prefer maths to actually just using maths to do something else, then maybe consider studying maths. But I'm going to talk about physics and engineering. So to give you an idea of the kind of modules and the kind of level of specialism that you get in studying these subjects, just thought I'd start with maybe examples of modules that I studied in my first year. So I had 4 papers in my first year. First one was mechanics and thermofluids, then structures and materials, circuits and electromagnetism, and then a maths paper. So that was 4, all quite broad topics. It will be the same roughly across all kinds of engineering courses. And then there'll be a few practical skills on the side, maybe some kind of like drawing both by hand and by computer, and programming. Programming is taught in all maths and physics courses these days. The language that is used may vary by course and by university, but programming is really handy, just if nothing else, just in terms of like doing calculations for you and visualizing data. It's a super useful tool. And now examples of my 4th year modules where I am now, much more specific. Renewable electrical power is one of them, sustainable water management, nuclear fusion and fission systems, and even some kind of more what we call management modules. So accounting and finance is one of them, these kind of more businessy ones that you're able to do. And these are all ones I've chosen. In my case, I chose from a kind of list of, I think, nearly 100, maybe a bit less, maybe 80 modules across that I could choose from, and I could pick and choose. I didn't have to even pick like civil engineering. I could just pick like a few civil engineering modules and a few from other places if I wanted to. So really, really like personalizable, and that tends to be the same across all like later years in physics and engineering courses. And I also have a project, which is very commonplace in terms of like 4-year courses like engineering, where in your last year maybe half your time is spent on this project, and you're the only person doing this project. And it might involve a lot of lab work. Mine personally doesn't. Very handy with coronavirus. So mine's looking at the emissions of wind turbines, for example. So quite specific. Write a big report about it in the end. A bit like a kind of a master's thesis for a kind of undergraduate equivalent of that. So what does actual studying involve? So, okay, I'm studying maths, but at school you sit in a classroom and then you do some work and then you're in a book and you go and do an exam. And actually, it's probably more similar to school than any other subject when we talk about maths and physics. Lectures, you'll have lectures, and That's where material will be essentially introduced to you. There'll be a syllabus, and the lectures will have like handouts. Maybe you have these in kind of maths and or at least physics and science subjects at school. So you're not writing all the notes yourself. You might be annotating, but diagrams and material will be provided for you, maybe in paper or maybe online. These days everyone tends to use a kind of tablet. I've got a little pen for writing on mine here. And then based off that lecture material, you'll have kind of different lectures, different courses. There'll be like problem sheets, most likely, so kind of lists of questions for you to work through. And there might be a seminar, or in Cambridge for me, supervisions, where I can go and like ask questions, find out how to solve these problems if I didn't know, maybe kind of stretch myself further. And exams would be very similar as well, and there'll be kind of like past exam papers as well that you could practice, just like at school, really. And then on the side, there'll be lab sessions. Maybe the labs are kind of designed to reinforce lecture material, or maybe that kind of practical skills that are actually completely unrelated. And occasionally you'll get like an essay or a presentation or something, but that's less common in my experience in first year courses. Fourth year basically depends on what you choose. You could end up very similar, or you could go down much more of a different route in terms of the modules you pick, and whether they're like more written courseworky things than exam problems. So in terms of timetables, I think kind of infamously engineering and physics have fuller timetables, much more structured. Certainly in my case, in my first 2 years, it was basically 9 till 1 in the engineering department every day. Occasionally, and that would usually be like 2 hours lectures and then a 2 hour of something else. Maybe that was a lab usually, or something like that. Or sometimes maybe there'd only be the 2 hours of lectures, but then like during weeks when we had like a bigger project going on, maybe a bit more 9 to 5. But it's worth noting that the idea in universities generally is that every course takes the same amount of time. Whether that actually ends up happening, it depends on the student, maybe. But if you are doing a lot of 9 to 5, I think the idea is basically that there's not too much to do, like if anything, outside of that time. And actually the amount of workload you do actually will vary week by week. So if you have a week where suddenly you have lots on, then it's going to be a bit busier. And inevitably things tend to get busier at the end of term just because, things pile up. But in general, well structured. You don't have to manage your own time quite so much. Still a fair amount though. Usually you'd be looking to try to aim to do your individual work in the afternoon. But you can still make it work around you. So obviously you'll have your fixed hours, but everything outside of that, if you don't want to do it kind of on an afternoon, you can do it on a weekend or an evening, whatever floats your boat. And assessment tends to be exams, at least in the first few years, in my experience. There might be some kind of like marked lab reports and things like that, but usually they're kind of ticking the box exercises, at least in the first few years. And so in terms of tips for applying, I really recommend you maybe consider learning some programming. Everyone gets to learn to program at university, but I really, really wish that I had actually really engaged with programming rather than avoided it before coming to university. It would have really helped me out, and actually it's really fun. So and if you're looking for a programming language to learn, Python is free, really well used, and it tends to be what's taught at universities anyway, so that's a good starting point. You need to not be afraid of maths. You need to enjoy maths ideally. It's used universally. It follows on quite nicely from kind of further maths and maths at A-level at university. You need to make sure you're comfortable with that material before you start and when you're applying. And then any competitions, lectures, masterclasses, summer schools, all of this stuff is a gold mine for personal development, experience, university application help. It's brilliant. So get involved with all that. And those of you doing back individual investigations, try and do it on something you're interested in this area as well. That'll help. And maybe just the final word on career types. Obviously, if you want to be an academic in these subjects or a scientist or an engineer, these are the perfect courses for you, but it's not the only thing, right? Also, students who go and work in the finance sector start in engineering because it's very, and science, very analytical. You're good with numbers. It's quite a rigorous course, so just kind of personally, you develop some really good kind of time management, motivational skills. And then again, there's all kinds of things. So you're looking at me who maybe might not go and work in engineering, doesn't want to go and work in finance, but would consider something completely different, maybe in government, civil service. So even like in my fourth year, you can say, I'm not 100% sure what I want to do, but I'm really glad I studied engineering. It's given me some fantastic skills, and I get to work about kind of causes I really care about, like climate change and things. So it's fantastic, and I really recommend it. So good luck.